So my name is Andrea, and coming from Switzerland, University of the EPFL, and from the lab of Semyon Malamud in the Swiss Finance Institute. And today I'm going to present Benign Autoencoders, or genuine autoencoders, as someone has said before. It works as well. It's a joint work with my advisor, Semyon Malamud, Andrea Shrimps, Giuseppe Matera, and Antoine Didichet. So let's start with the motivation of this work, or the motivation of this paper. And I'm going to give a small introduction about a subfield of machine learning, which is called learning representations. And in this field, our goal, our aim is to learn the best representation of the data that are given in our task. And I'm showing here an image, a convolutional neural network that tries to find the best features about this image. So borders, shapes, depth, and colors, and so on and so forth. Another example of learning representation, we find it in natural language processing, and now I'm exploiting ChatGPT. And by asking him write a poem about University College London, UCL, we don't know the representation that this AI will use, maybe a bag of words, but it will produce a nice poem out of nowhere, because it was trained in a task-specific manner. So the main goal and the main question of this paper is to how best represent our data that is usually embedded in high and complex dimension. And we will show in this paper that in information theory is known that processing data usually always leads to information loss. But in machine learning, we always process data, we feature engineer, but we actually gain some accuracy or better performance models. So let's move on to the theoretical backgrounds. And I will start talking about autoencoders. Autoencoders are generative models that were largely used to learn representations because they compress with this bottleneck that I'm showing in red to actually learn how to best represent the data in a small and compressed space. So from top bottom, we know that the first part is composed by an encoder, which is just a map from the original data space to a latent space, Z. And the dimension of Z lives in a smaller and lower dimensional space than the original data space. And then at the bottom, we can find a decoder, which is a map back from Z back to the original space. And the composition of the two, we obtain the autoencoder, exactly. And in the classic encoding problem, we use these autoencoders to best reconstruct our input data. In this case, I'm showing this image, this dog, and the goal of this autoencoder is to minimize the loss between the reconstructed data and the original data. The loss can be mean squared error, binary cross entropy, and so on and so forth. And another type of autoencoders, we find them in probabilistic autoencoders. In this case, we are trying to learn the probability distribution that generates the data. And for example, if the probability distribution is just a normal distribution, we would like to learn the mean and the standard deviation that generates these samples. Encoded in this smaller space, sample a random variable Z conditional to this conditional probability distribution and try to reconstruct the generative, the probability distribution that generates the data. And the optimization function is to minimize the reconstruction error again, but it's about probability distribution. So we can say that we are minimizing the distance between the reconstructed probability distribution and the original probability distribution, with the constraint that the marginal distribution over the latent space Z is exactly the same as the original probability distribution X. So now that we know about autoencoders, the probabilistic autoencoders, let's look at the classic machine learning problem. So in a classic machine learning problem, we are given a data set composed about a set of X and a set of Y. Usually Y is the label and X is our input data that we have to classify, for example. And here I'm showing the MNIST dataset. So in this example, X is a matrix that shapes the number, the digital number, and Y is the label. And usually we have a classifier, a model that, in this example I'm showing, it's a neural network, and its task is to classify, given a data, predict the label, for example. And then we have a training algorithm. A training algorithm is a mapping from the trained sample to an estimator. So here I'm showing the most common and training algorithm used for neural networks, which is the stochastic gradient descent, where the model evaluates and computes some accuracy. We could take the gradient and we update the weights and so on and so forth until we are fine with the fine tuning, let's say. At the end of this training algorithm, we will be given estimator, which are the optimal parameters to set this neural net. So an example is a simple example is in the rich regression with penalty lambda. The solution of the objective function will be exactly our estimator. And this is important here to notice that our estimator is highly dependent to the trained sample. So the training algorithm goal is to minimize the expected test loss given a trained sample. Now, if we define Wx as the negative expected loss given the trained data, and we plug in into the previous loss, we obtain the loss, which is defined as the negative expected loss given Wx. But instead of feeding, instead of evaluating W on X, which is the raw data, we will feed the reconstructed data. And we call this the optimal probabilistic autoencoder problem. Oh, sorry. And so basically, we will see in the empirical parts that we will construct an autoencoder. We attach at the end a classifier, and we will try to find an optimal probabilistic autoencoder. And the task of this autoencoder, we call it meta learning because by classifying task manner problem, we will learn the best representation of the data. So now that we have all the tools, I can formally describe the problems. So on the left, we have the optimal probabilistic autoencoder problem, which is the negative supremum of the expected value of the W function evaluated on the reconstructed data. So the constraint is the probabilistic autoencoders constraint, which again are the marginal probability distribution over the latent space should be equal to the original probability distribution. And on the right, we have the deterministic of the autoencoder, which is similar, which have a similar objective function to the probabilistic autoencoder, but in this case is deterministic because the parameters live in a discrete space, and then they are they are evaluated at a deterministic way. And since every deterministic autoencoder can be described as a probabilistic autoencoder, we always have that the loss given the probabilistic autoencoder will be lower or equal to the deterministic autoencoder. So now we look at the loss function W evaluated at reconstructed data, and its shape is very important for us. What is the structure of this loss function that we ask ourselves? And I will give a fresher reminder about Jensen Inequality and its nice properties, of course. So basically, if we have a convex function G, and if we take 2 points, x1, x2, we will always have that the convex combination of the function evaluated at 2 points will be always bigger or equal to the value of the function evaluated at the convex combination of the 2 points. And this property can be extended for probability functions. And we will always have that the expected value of the function evaluated x will be always greater or equal to the value of the function evaluated, the expected value of the random variable. So this is the intuition about the paper. If the loss function W is convex, then the compression will be always suboptimal. And this is given by the Jensen inequality. As we can see, on the left-hand side of the inequality, we have the expected value of Wx. And on the right side, we have the W evaluated on the after the compression. So the compression here is always suboptimal if the W function is convex, whereas if it's concave, then the code space will be a single point and compression will be always optimal. But what do we have here? That we know that the neural networks loss functions are highly not convex and not concave. So the optimal code space, which is the compressibility of the original data space, is so the optimal code space, the compressibility latent dimension, is not the original data space or not even a single point. And the more highly not convex, not concave is the loss function, the more we can regularize and the more we can compress the original data. So this is the main intuition. We use Jensen inequality to state that in machine learning, data processing inequality can be misleading, and processing data is actually beneficial. And that's why benign autoencoders. So to show some theoretical results, first of all, we ask ourselves if a deterministic autoencoder does it exist. So if the code space Z is finite, then there always exists a k-finite deterministic autoencoder, which we call BAE, which is partitional. Partitional means that given a sample for one label, the autoencoder will just put it in that cluster. So now that we know that a deterministic autoencoder exists, we also prove in the paper that optimal probabilistic benign autoencoder always exists, and it can be approximated as the limit of the discrete one. Finally, to follow more theoretical results, I need to define nu plus A, and A is where A is a symmetric matrix. So nu plus A is the number of non-negative eigenvalues given a matrix. Then another definition, we use this subscript XX to denote the Hessian of a matrix, in this case, the function of W. And then the following theorem states that for any optimal probabilistic autoencoder, the latent space that is projected original space is a subset of a new dimensional Lipschitz manifold, which means that the latent space is upper bounded by the number of positive, non-negative eigenvalues of the Hessian of W. So we have some information about this latent space. How does it look like? And now I need to admit. Okay. And finally, if the original data is convex, we can show that the loss of the probabilistic autoencoder is actually equal to the deterministic autoencoder. So to sum up, before moving to the experiments and the empirical results, I talk about feature learning representations, which is the subfield of machine learning that tries to understand how to best represent data before feeding to any classifier or model task manner. Then I talk about autoencoders, probabilistic and deterministic. And in the historical literature, autoencoders were trained unsupervised. We call it unsupervised because where they were used always by trying to minimize the reconstruction loss and not as a task-specific manner before feeding a neural network. And we have defined the optimal probabilistic autoencoder problem using meta-learning. So moving on the experiments and then the empirical results. we have built in the experiments of this big neural network, let's say. And I'm reminding here the parts of each component of this neural network. So encoder, latent space, decoder, and neural net, or classifier. We call it also a classifier. And then we apply this training algorithm. So the novelty here is that we can see in blue and in orange that the objective function of this neural network is not only to how well does it classify if it's a classification task, but we put also the reconstruction error, so that we are able to tune it and to teach the neural network how to represent, how to best represent the data. And of course, we have a latent space and a bottleneck in this neural network architecture. Then we use a convex combination, as we can see, WNN and the WAE lives in 0, 1. And if someone wants, so some of the critiques is that this is just a gigantic bottleneck, neural network with a bottleneck, but by setting that, but we experiment, in our experiment, we always have seen that the setting WNN equal to 0 and WAE to 0, which gives us a very similar, a neural network, always loses against our setting that is by setting WNN equal to 0.1 and the compression weight to 0.9. Which means that we are giving more weights to the reconstruction loss than the classification task. And of course, and also, moreover, we are training this neural network with the odd and even epochs. For example, in the odd epochs, we can see that we are optimizing all the parameters, whereas in the even epochs, we are optimizing just the autoencoder. That is punished also with the task classification loss. So our experiments are pretty much simple. Our benchmark are, first of all, a simple classifier neural network on the left. In the center, we have an unsupervised autoencoder that reconstructs the error and then feeds the classifier. And then in the end, there is our implementation that we have just seen. We first evaluate our setting with a simple regression task with synthetic data constructed with a sigmoid, basically. All the x, y, and the weights are sampled from a standard distribution function. And what I'm showing in the table is the mean squared error in this regression task. And then we see that the benign deterministic autoencoder outperforms both the unsupervised autoencoder and the classifier. Sorry, I need to admit another guest. And then, of course, we try our classifier on classification tasks like MNIST, same setting. We noise the dataset with a standard distribution noise vertically, and we show that we actually gain 2% in each setting. And finally, we also do the same using the famous MNIST, fashion MNIST dataset. So to conclude, so we formalize the optimal probabilistic benign autoencoder problem, prove that compressing or processing the data under benign autoencoder condition is always optimal, and conventional wisdom that stated that processing data always leads to information loss is wrong. It's a typo, it's wrong. Provide an empirical tool to implement benign autoencoder. Autoencoder should be trained in a supervised task-specific manner, and show that our implementation outperforms the classical approach. So thank you so much for your attention. I guess that